So we're here today to talk about the applied machine learning environments at Maxar. To start out, we really want to start talking about what are the problems that we're trying to solve here at Maxar, right? And what are the sort of challenges when you want to start solving problems at scale? In other words, if you're looking at terabytes and terabytes of information every single day, and you would like to produce detections on that global daily take of satellite imagery, what are the kinds of challenges that you need? We'll talk about, what are the sorts of structures within an organization that you'll need to start considering. And we'll go into each one of those different sub-teams and explore how and the types of technologies that they'll develop in concert with each other in order to...
Would you please increase the put in presentation mode so it's like larger?
Yes, absolutely. Let's see.
Present over there? Yeah, perfect.
There we go. Okay.
Thank you.
Perfect. Okay. So we'll talk about, how the machine learning engineering team is going to democratize the model development process so that many different people who have a different set of skills are able to engage with each other. We'll talk about the ML ops team and how you go from zero to a grid scale compute in about 20 minutes. How do you build these large scale infrastructures very rapidly while minimizing the amount of people you need? Then we'll do a quick demonstration of how those technologies come together. And we'll talk about our data science services team and how we stay in touch with customer needs by solving real world problems. And then we'll show a real experiment that we run at scale using this kind of technology. And we'll talk a little bit about that. I think Fabio may have spoken a little bit about the effects of spatial resolution on vehicle detection, but we'll kind of take more of a perspective around the scale. And then we'll go into questions as well. So, and hopefully we kept it fun. Way that helped a lot. All right, so what's the problem? Well, Maxar mostly earns its profits in an amount that's proportional to the number of insights that we can give our customers over time, right? So the more detections that you're able to deliver that are of high quality globally, all over the world, the more money that Maxar is going to be able to make, right? And we've found that our customers need those insights at a far more larger pace than Maxar can provide that to them for a number of reasons, right? Now, what's stopping Maxar from being able to do all the detections all the time around the world, right? Well, what we found is that one of the biggest bottlenecks, the biggest preventers, is that we have to source really expensive labor to hand engineer models. And what does that mean exactly? Well, when a person is able to execute machine learning at scale, it means that they have to become a subject matter expert. They have to be a statistician. They have to understand programming of Python. They have to understand deep learning, and they have to understand how to get the resources, the compute resources, all in one place at the same time while solving large data problems. And when one person figures out all of those things, unfortunately, that means that Google will hire them for $2 million a year, and it's impossible to source the labor, right? So if you want to be a millionaire, go learn all of those things and then go apply to Google. That's a great way to do it. But that is not a really good defensible business model for Maxar. So we have to figure out a way around this expensive labor. The other thing is that there's a valley of death between experimentation and production pipelines. So, if you're on the bleeding edge of deep learning right now, and, particularly for imaging, you're working with transformers and you're building out synthetic data and you're doing GANs and you're doing all this exciting stuff, it's very difficult for people working in that environment when they're finished with their research for it to be pushed into production at scale in a way that folks can then pay for it and ultimately, support continued research, right? We also have difficulty keeping track of how monitors perform over time. As you know, if you develop a model on satellite imagery to do, let's say, object detection, that may be good for a little while, but the world is constantly changing. And so the underlying phenomena that you're trying to model will also change. And then therefore your models will reduce in performance over time. So how do you keep an eye on that? How do you keep track of that at scale? Well, we found that we didn't really have a set of tools to do that just yet. And so, we needed to find a way to fix that problem. And then the other half of it is just the sheer scale of data that Maxar ingests in the global daily take necessitates an ML solution. I mean, if you look at the amount of data Maxar collects every day, it's upward of 7 terabytes per day, every single day. So imagine if somebody gave you the keys to like 4 warehouses full of imagery, and you had to go and find through each picture, all the individual objects that your customers care about. It's kind of trying to find a needle in a haystack, and that haystack is getting bigger and bigger every single day, right? So the problem we're looking to solve then, how do we intend to solve that? Well, the applied machine learning team at Maxar solves it by relying on commoditized technologies. So the amount of available technology that's in the world is ever accelerating and more and more powerful. We plan to leverage Maxar's GIS expertise. We've got a lot of really great geographers and subject matter experts who really understand the physics of this domain. And then from that, we want to generate a shared model development, sustainment, and enhancement tool that anybody can use, that folks with just specific types of knowledge can use, so that you don't have to be that $2 million a year 10x engineer in order to engage and build profit for the company, right? And then of course, through this, we want to increase the volume of reliable insights that we can deliver over time in a sustainable way, right? Okay, let's step out of the boardroom. This is the slide that you give the CEO so that they give you a lot of money to build a team like this, right? But let's step out of that for a second. When we try to solve this problem, we usually don't try to start solving large problems like this from scratch, right? We look around at the world and we say, well, what have people done in the past? Well, around 2017, about 5 years ago or so now, Google published this paper called MLOps Continuous Delivery and Automation Pipelines in Machine Learning. And in that paper is this graphic. And this graphic is probably pretty familiar to a lot of people in this room because it kind of went viral over the last couple of years. And the point it's trying to make is that the machine learning code itself is really just a couple hundred lines of code, right? In a lot of cases for the model. Around the machine learning code are all these different components, right, that folks need to think about in order to support large-scale machine learning. And that includes everything from data verification and validation, through model analysis, through the serving of infrastructure that might happen in the cloud, the very tight understanding of metadata, and then ultimately monitoring of these systems as they happen in production, right? I think that not everybody will solve their large-scale machine learning problems as Google does. We don't all have their deep pockets, of course. But this is kind of a clue that we need to create this separation of capabilities from around these different skills, because each of those different boxes will require a different type of engineer, right? So within my team, we always try to set up a very practical goal around this. What are we trying to enable for folks? And we said that what we'd like to do is to be able to hire a data scientist, and within 1 hour of joining, we want them to be able to download and explore imagery, understand the metadata for data science purposes. We want them to be able to engineer data sets, because we really believe that actually the future of a lot of the remote sensing space is around your ability to characterize and understand data to a very fine degree, even more so than the model development itself. And then we want the modeling that gets conducted to be production ready from the moment that it's finished, right? So that was kind of the target that we were trying to hit as a team. And ultimately the idea being reduce the technical burden for each individual to operate at scale, right? And to solve that valley of death between research and production. Okay, so this is roughly the team that we came up with, that we decided need to solve that problem, right? We've got a machine learning engineering team, we've got a machine learning operations team, and we've got a data science services team. And we'll talk in depth about what each of these teams do and what they do in the coming slides. All right, so what does your machine learning engineer really do? Well, we sort of think of the machine learning engineer as a person who builds a unified set of Python tools that data scientists can use to develop, maintain, and improve machine learning products. And that's really to say that a lot of data scientists, when they come to the game, they tend to understand Python, They tend to understand how to use Jupyter notebooks, but they don't really want to have to resolve or really have to understand a lot of this kind of skills on the side around accessing databases, around user authentication, around understanding how to very rapidly move and query information, right? Those are kind of skills that are secondary to what we believe most data scientists, like really get excited and love to study and focus on, which is kind of questions around the properties of that data, or how do you take advantage of the properties of that data to come up with decisions at the code level, right? So this applied machine learning team will really focused on trying to build that unified set of Python repositories and create a software that seamlessly integrates into Maxar software offerings, so that when they're finished, things will just work in production. And more specifically, it's trying to reduce the burden of worrying about production issues from that person, right? So that they can access large-scale cloud infrastructure. Okay, so how does that actually work in practice? Well, when you go out into the real world, right, you'll usually still have subject matter experts, because even if you go to school and we study, multi-layer perceptrons, we study ResNet, and we understand all the concepts around backpropagation and the chain rule that leads to, that understanding of how we can adaptively improve our models, there's still somebody usually in the real world that is dealing with a use case. They're really interested in enabling some sort of activity, right? And the people who are out there, they may be physicists who really understand weather patterns, or they may understand the physics of light, or they may understand, different properties about construction vehicles that dictate the pattern of life for the construction of buildings, right? So these are folks who really understand the target that you're trying to achieve, and they understand at a very deep level. Like we're talking about hydrologists or physicists or people of that kind, right? So if you look at this picture on the left, the part that's excluded from the brackets, that's sort of like the subject matter expert. So they may really get an idea, understand like the target ontology. They may understand, okay, we're looking for vehicles or planes or cars. They may understand the differences between residential and industrial regions in the country. So, they may understand the properties of glaciers very precisely, right? And so they really kind of think about the target space in terms of labels and tags and things like that. So in their use cases, they may have mapping as an option. They may have object detection. They may want to track, let's say, whales as they travel across the world, right? Things like that. And they also kind of roughly understand the analytics that you're going to require to enable those use cases. In mapping, they really worry about semantic segmentation. In the tracking of whales, they're really worried about object detection. So they have that kind of understanding too. And then finally, in the environments that they're in, they have access to a very broad variety of different kinds of data. They may have electro-optic or infrared imagery. They may be looking at SAR, synthetic aperture radar, or even like non-pixel signals intelligence, or electronic signals, or let's say pings from a cell phone when folks are accessing different apps, right? And so they really understand the data that they're kind of playing with or have access to. And when they do that, they generally are able to harvest that data and extract information from those existing sources. So they're looking to label that information or make queries to existing databases of information to create what we call extrinsic and intrinsic data, right? So when they go and they scrape a database or they go and label it directly, the intrinsic data really relates to data about the properties of the sensor, right? So this may be things like the RGB histogram, the red, green, blue histogram of the pixels, right? It may be information about the saturation points from the sensors and things like that. And the extrinsics refers more to the label properties themselves. So if you're doing building extraction, for example, it may be, the distribution of the building sizes, the separations between the buildings, the actual labels themselves, right? So they're really kind of getting into the weeds of understanding the model that you're going to ultimately try to build. And they really have a strong idea of what's signal and what is noise in that information. And usually they'll pass that information off into some kind of data lake, right? So If they're very unsophisticated as a customer, that data lake may be just a folder on a computer somewhere. If they're more sophisticated, perhaps they're using, Parquet and it's stored on S3, or, they have some sort of big query that they're able to access these very well organized sources of data. So that's sort of where, you're talking to your subject matter expert and they have, access to all of this information. And to me, that's sort of where the applied machine learning engineering role begins, right? At that point, we're bringing to bear a set of skills where we try to understand the feature space. We try to do search and discovery or training set generation, right? And that's where perhaps you have an understanding of the statistical distribution of the data set that you're trying to create. And then the machine learning engineering team builds a set of tools that allows you to query that existing data and perhaps do some sort of Monte Carlo sampling to generate thousands of candidate data sets that you can then select the perfect one for when you're trying to do your eventual model development, right? It also covers issues around, like, let's say, exploratory data analysis. So you want to create a very simple way for users to play with data and do something meaningful with data as quickly as possible, so that you can understand, what is the difficulty of the modeling process. I think a big part of that model development is building a human intuition around the data that you're looking at to see if, modeling is even possible. And this is particularly true in geospatial analytics, where you're looking at images of the Earth, right? It may be a little less true when you're dealing with hyperspectral spaces, but even then, having a good set of exploratory data analysis tools is something that'll help you really hone in on the types of models that you're trying to build, right? And there's also kind of a virtuous cycle here. So if you're looking at your data lake and you're trying to build models and it doesn't quite, you can't quite get the model that you need, you have to communicate back to these subject matter experts to go collect more information that you're missing, right? And so, it kind of points to the fact that when you build out tooling for a machine learning engineering team, you need to consider the fact that there needs to be feedback going back and forth between the subject matter expert and the data scientist or the machine learning engineer, right? Now, of course, it would be really nice if, a data scientist could very easily spin up machines and, describe experiments at scale. It's also equally important that in the APIs that you build, that a data scientist can pass to the engineering team specification for what an experiment should look like. So if you as a data scientist wanted to run, let's say, 1,000 hyperparameter settings for 1,000 models, the machine learning engineering team builds a very nice method or mechanism for which that can happen. So essentially ensuring that experiment design is a part of the tooling that will then go and use large-scale resources, right? And then finally, performance analysis is another enormous component of this, being very consistent with how we measure, the performance of models, and doing that in a way that's enforced by the infrastructure that you're building is pretty critical. One last piece here that is kind of related to that is the notion that, again, when you're done with your modeling, you want to make sure that your models work in production. And unfortunately, a lot of different production environments have very specific restrictions about what they can run. For example, if you are in production and the pipeline was developed using, PyTorch, 1.4, and you're developing models against 1.6, oftentimes you may not have access to the fundamental layers that in production that you do in your experimental phase. And so using this kind of methodology around building a repository, enforce model characteristics during the research and development stage, so that when you're finished with your modeling, it will guarantee to work for a set of target production pipelines. And that's actually enforced and communicated at the API layer by the software. All right, so that seemed like a lot, and it is. This diagram is the UML diagram that just describes how Maxar deals with data inputs into the applied machine learning engineering environment. So this seems like a lot of crazy rigor, and in fact it is. There's a lot that goes into making something very simple for a data scientist to use. And so I think hopefully we'll see that here. All of that UML, in a way, if you look in the middle here, you see there's a common order data specs constraints. That constraints is essentially a dictionary that can be passed into the architecture that you saw above and makes it completely invisible to the user while giving them an enormous amount of flexibility. And we can talk a little bit about that as we go through the demonstration. So what other things do we want our users to be able to do very easily? Well, we had mentioned that authentication was a pretty important thing, right? We want people to be able to log in and then not have to worry about, making SQL queries or worry about, authentication to access different data sources. So that's right off the bat something that this environment can offer, or is important to offer. We also want to make it so that folks can Maxar data holdings in a few minutes, not hours. In the company, within an hour, we're hoping that they can access this imagery, create data sets, and there's quite a bit of different types of Maxar data holdings. You don't just necessarily look at the pixels, but you also may want to look at metadata, at pan-sharpened image, high-definition imagery, or electro-optic imagery, or precision 3D type data, right? So when you have a system like that that makes it easy to access data holdings, it really speeds up your ability to go from data to decision for critical missions, right? And of course, when you're talking about these systems that have terabytes and terabytes of data, it's important to move just enough data every time. And I think human beings, we can be very blunt instruments in that we ask for everything, but a system like this might help you be more specific, so you can kind of pare down your data requests, so you're not trying to look at every piece of data in the entire world all the time, right? Okay, that team is also ultimately coupled with a machine learning operations team. And the idea here is, if you're sitting in front of a computer or cloud infrastructure, how do you go from nothing to grid scale compute, right? Your ability to take in terabytes and terabytes of data every day and do that computation. Well, as you can imagine, there's a lot of compute resources that are involved there. And there's a lot of rigor that would go into doing that. So if you want to deliver, a deployed Dockerized version of this machine learning environment, how do you do that, right? What are the kind of tools that you can use? Well, our technology stack is fundamentally built on things like Kubernetes. We rely very heavily on kubeflow pipelines. And mostly that is to provide our data scientists with a Jupyter Hub backed, an EC2 instance backed Jupyter Hub. And when we provide that EC2 instance, we load into it all of the different Dockerized capabilities that we discussed previously. And so therefore, if you're a data scientist and you want to spin up 100 machines, you can do that without ever looking at drivers or ever having to look at any sort of code to set up GPUs or the repositories. It just all comes for you out of the box quite easily, and we'll show you how to do that in a second. As far as data storage goes, it also sets up your data lakes and your S3 backed storage, and then as you develop and create Dockerized capabilities, this team would actually go and deploy that into an orchestration engine that would help you go through that process. So back to Google. How does Google think about MLOps? Well, this is another photograph from that landmark paper. Maxar has its own, but I'm not allowed to display it here, unfortunately. But what we have here is this idea that you have a separation between experimentation and production. In the top, we have the experimentation phase above that dotted line right here. And below, you have the production pipeline. I think what you might notice, though, is that they both have these blue boxes here, right? In the top blue box, it covers things like data analysis, data validation, data preparation, model training, model evaluation, model validation, right? And these are just the normal kind of steps that you might conduct when you're experimenting in data science. But what you'll notice is that this box is mirrored here in production, and that's by design. When a person is conducting large-scale machine learning experiments, you need to make sure that the environments are very easy to sync with each other so that when a person's finished, it will guaranteed work in that production environment. All right, so what kind of things are we looking to orchestrate exactly? Well, the model, there's sort of three major components that the MLOps team focuses on. The first is the model repository. So we basically create these large-scale data lakes that hold on to the models and their characteristics, and specifically a lot of metadata around how those models were produced. So for any given model, there's a recipe that is repeatable, and you can rerun in a deterministic way, repeatable way, to produce that exact same model if you had to start from scratch, from nothing, right? And so the model repository is very focused on saving and storing these models and making them searchable so that when you start getting to have thousands of models, you're able to find models that have specific properties and either fine-tune or auto-retrain against those models as a starting point when you want to do new development. The MLOps team also focuses a lot on orchestration at scale, and that is about spinning up thousands of machines at a time so that you can do data set engineering, data creation, model serving, and training. And to do this in a pipeline kind of way that is parallelizable so that you can do that while we're still young, I would say. And we'll show an example of that in a few slides here. And then finally, probably the largest component, which is the least tractable, is the notion of the feature store. So knowing exactly what kinds of features to extract from existing data and storing and serving them in the most efficient way using tools like Arrow and Ballista to make sure that you can automatically generate thousands and thousands of data sets in minutes so that you can really rapidly experiment. I mean, I would say the data set generation component is a very, very difficult traveling salesman problem where you're trying to find the N samples of this much larger set of data that most optimally fit your statistical distribution of the target data set. And so in order to do that, there's no closed form solution. You have to just use a form of brute force, essentially, to automatically generate a Monte Carlo sample massive amounts of data sets so you can find ones that are kind of closest within the box for you. So that's kind of how the MLOps team focuses on. This is actually a photograph of our current most simple cluster distribution. And so effectively, the MLOps team will spin up automatically a set of dual nodes that take in requests and automatically scale compute as a function of requests that are driven by our applied machine learning repository, essentially. Okay, so what do you want to do then as well when we talk about like serving out different types of components for pipelines, right? Well, one of the things that folks tend to like to do in production is they like to take data, transform it in a variety of ways, and then execute inference and produce and send the derivative data products into production for use, right? So there are many different kinds of pipelines like this, but in particular, this one is important because it is actually probably the most commonly used pipeline today in our data science workflows. So when a user needs to describe a pipeline like this, the infrastructure that's written makes it very, very rapid in order to do that. In this case, this particular pipeline will be looking at imagery that exists, querying it, running orthorectification, doing a registration, what we call P3DR, which is a highly accurate co-registration of your satellite imagery to some global frame of reference, and then ultimately producing detections for exploration purposes for our users. Now, the key about this infrastructure is that it's very efficiently managed so that you don't end up paying through the nose, paying an enormous amount of money for hardware that is just sitting idle or spun up, right? So you're able to monitor the usage of the compute for these different purposes, even if it is at scale. And you're even able to be predictive about how much you believe it will cost you so that before you hit the enter button, you know exactly what it's going to cost you and you're not worried about the price tag, essentially. And that's kind of a mechanism that helps us bill our customers, essentially. All right, so once you've run those detections, you sort of want to share them with the world, right? And so the other characteristic of these applied machine learning pipelines is that we want to make sure that the form that the data takes is exportable and communicable to a lot of different existing workflows. So one thing that's very common within the geospatial analytics world is that they use a lot of common tools like ArcPro or QGIS on the free side. Maxar Maps is a Maxar IP that essentially is very similar to ArcPro, but is more tuned towards Maxar. And then, these other kind of various GIS tools that folks might want to use. The other thing to note is that if we go back one slide, each one of these components in this pipeline will produce a data product, and that data product is entirely available to users. So at any moment, if a person didn't want to go all the way through inference and only look at the inference, they could also access the output of an orthorectified registered imagery, right? So they could look at each one of these stages within this pipeline and access it from S3 in an OGC type way, Open Geospatial Consortium type way, so they can be ingested into these common workflows. Now, why is this important? Well, effectively, this backend enables what we call a low or no code environment for analysts to use. And, for better or worse, a lot of people don't have the broad data science expertise, but by using a tool like this, they could definitely start using some of the products of data science in order to make decisions about their use cases and their missions. Okay, so I think we're just about ready for a quick demonstration of the AML platform. So can we see this screen? Did we switch?
I still see your slides.
Oh, you still see the slides. Okay, hold on.
Yeah.
Presenting. I'll just do the entire screen here. Okay, so do you see something now?
Yes.
Yep.
Okay, great. Okay, so what do we want? One of the things we want to kind of remove, or is a good thing to remove from your users, is again, we want to separate them from the idea of building different environments. So one of the things that we've achieved now with this infrastructure is that you can very quickly spin up a machine. You can select the Docker container that you would like to put behind it. You can pick the number of computers, the amount of memory. You can determine the number of GPUs that you'd like to run, right? And you can go ahead and kick this off. And roughly in about 40 seconds or so, sorry, I got to authenticate again. Okay, sorry. And then roughly in about 30 seconds or so, you can build a machine without ever having to touch, drivers or anything like that, right? And when you click connect here, it'll spin up a Jupyter notebook as this one is, and give you kind of access to the entire environment from end to end. And so in this case, we have a Jupyter notebook that is able to build that production scale pipeline that we talked about. It's able to look at the global daily take, all the imagery from every day, and very rapidly able to run those set of processes that we described all the way through inference, right? So what are the different components about that? Well, we definitely want it to be very easy for people to describe and search through the data, right? So what we do is we focus a lot on something called manuals, constraint manuals. And a constraint manual is basically everything that you need to know about a data provider that is settable by the user so that they can describe a lot of optionality and then essentially query the data from a particular data provider. In this case, this is our Content Hub data provider, which is a metadata provider about the imagery itself. So it does not provide imagery, but it provides information about the imagery. And basically, it's a very powerful API because you're able to have a lot of optionality, but mostly you want to focus on the end and start date times, so the end date times, right? And also the bounding box that describes the area of interest. So if you go ahead and look at this update of that dictionary, you see that we've added a bounding box. We've added a start and end time. And we've also added like these queries because we only want imagery that has less than a certain amount of cloud cover, for example. And then quite rapidly with a very simple call, you're able to request data with that manual and produce, an output like this. So by looking at this red bounding box, it looks at all the images that intersect, that we have in our catalog that intersect with that red box, and it'll go ahead and produce the footprints that they create, and also provide you some of the metadata that is available for that particular imagery. If you click on it, we'll even give you like a little sub thumbnail of the image. And so this is really just kind of trying to promote that people, get really hands-on with the data and start using it and looking at it in more and more accessible ways so that they can make decisions about their data in real substantive ways. Okay, once you have the cat IDs, then you can actually order the imagery to move it. So the metadata is very light, and so it's very easy to move. The imagery itself, some of these scenes can be over 20 gigabytes in size. And so making a full order of that imagery is a weighty decision. It's a decision you should take your time and make sure that is correct, right? And so similarly, again, we use a constraints file, a manual, essentially, to describe how we request data from an imagery provider. And in this manual, it contains every single different type of way that Maxar produces data. And it can be quite verbose. There's quite a lot of different things you can do. You can name everything from the type of compression that you would like, all the way to the number of bands that you would like. You could even decide if you want to just use pan or SWIR. You can create different types of data products that are registered to the Earth in different ways. You can decide to use mosaics if you'd like. There's just a huge amount of optionality in some of these data providers. But when it comes back down to it, all you have to do is update, a few parameters here. And again, you'll conduct a request as you would before. And that data, then the repository, the machine learning operations infrastructure will go off and download that data for you. In this case, we picked one of the cat IDs from the images above. We had decided to apply a comp, atmospheric compensation, and then we've described like a bit depth and a number of bands and the registration amount, right? And most of this is set up in kind of a default manner. So we kind of have the order of operation that data scientists would mostly use when they want to access Maxar imagery. But in this case, we're just kind of showing you how you might update some of that imagery up front. So you can go ahead and place the order. I actually already did this before, so it'll check with the repository to make sure that you maybe already downloaded this data and you don't need to do it again. And then you can actually, since these things do take some time, request the status of that order to see if it's, what kind of state it's in. And then once you have the imagery, you can start doing exploratory data analysis. So very kind of similar to some of the ideas in Content Hub. When you do EDA, you really, you give it some set of cat IDs, and it'll return to you all of the metadata associated with the cat IDs. This is an enormous amount of metadata. I believe every image at Maxar contains over 240 fields of metadata. And that includes everything from the look angle of the satellite when imagery was collected, all the way through to the internal camera parameters, that might have been on the image, right? And even some derivative products like the cloud cover and things like that of a particular image. Once you have kind of like that data frame, we have a few operations that we like to provide within the infrastructure, but we're also not prescriptive. So a person could come in here and write their own pandas data frame based analysis on the metadata, and that would be just as equally supported. You don't necessarily have to stick to the prescriptive methods that are provided. In this case, we're looking at an ability to view some of the rasters, some parts of the raster. And you can see we also provide some fairly simple kind of augmentation techniques so that it makes it easier for folks to see it. In this case, we're providing a histogram equalization here, or sorry, percentile stretching here, so that the image can go from dark to something a little bit more appealing to the visual eye. You can also do very simple analysis like create histograms from that metadata. In this case, we have an RGB histogram for that particular image. But we've also built, in a very automatic way, built out other kinds of histograms like the look angles across thousands of images and things like that to provide answers relatively quickly. Okay, so once you've decided on the data that you want to process, then we can go about creating these large-scale pipelines that we've been talking about, right? So in this case, again, we go back to our constraints file, our manuals, and we have a lot of optionality around this particular type of pipeline. Essentially all the decisions that you can make around the different kinds of registration, the different types of pre-processing that you might want to do in order to execute the pipeline. And so roughly speaking, with a few lines of code, off you go, you set up the pipeline, you tell it what kind of model you want to run, you tell it the confidence score and the non-maximum suppression, and you give it the inputs, the name of the cat ID, and off it goes. It'll kick off that pipeline. When it's finished, or when it starts running, you can actually keep track of the details of the experiment by clicking here on the output, and here we have the pipeline itself executing. As we said, kind of each stage of the processor provides you a lot of details on the different components and all the metadata that kind of is associated with the different operations that might run. And so, why is this important? Well, if the pipeline stalls or breaks or whatever it might be for whatever reason, all of that information is logged and stored so that people can update the code if they find bugs, right? Then of course, once the pipeline is complete, this is actually the result of that image. That's the image itself has been printed up, and the output file from the inference has been laid over on top. And you can see that it's finding these military vehicles on the imagery itself. So what you'll also notice is that this is on a Slippy map. So it's fully OGC'd, but also the outputs of this can go into a tool like QGIS or whatever you might want that might be kind of more in line with your existing workflows and tools. Like, we don't want to be very prescriptive to the analyst on how they utilize this data if they already have workflows that they're very comfortable with. And so this kind of view is really purely just from a data scientist perspective. Okay, so that consists of the demonstration. That was one example of how you can build very rapidly pipelines that work in production. But there's a lot of different types of things, lots of different types of machine learning that data scientists like to conduct at Maxar. So as a result, I think we have something on the order of 125 or so data scientists at Maxar. There's about 6,000 people in the company. So yeah, it's about that much. And they do an enormous amount of different missions. They look at object detection. They look at land use, land cover. They do scene classification. They've done synthetic data generation. They've even looked at quantization-aware modeling so that you can put models in space on satellites. And so there's quite a bit of variety in the types of work that people do. It's difficult to meet all of those missions at once. So we thought it was critical in the organization of our teams that we create a data science services team. And that team is relatively small. We're talking about 5 or 6 people. And mostly what they do is go around the company and find the use cases, the types of machine learning that are most important to our customers that have not yet been integrated into this framework, right? And so they're really kind of on the bleeding edge of the research at the company, but then also the implementation of that in a production kind of scalable fashion. So they have a very exciting job, right? This is roughly how those teams interact to make sure that the work that they conduct actually comes back into those teams and gets disseminated out into the world. Okay, so what is an exciting project that they've taken on, in this process? Well, one of the exciting projects that they've taken on using this process is a project we called Project Watchman. And it really was looking to analyze the effects of spatial resolution on vehicle detection. So we wanted to see if you go from a very high resolution image like a 7-centimeter image and went down to a 60-centimeter image, at what point does the model fail to do well? Said another way, we're looking for the Nyquist rate of object detection for cars, right? And now, why is that important? Well, it'd be really good to know what kind of performance you can expect from a model at different levels of resolution, because as the imagery gets larger, it gets more expensive to transport it gets more expensive to store, it gets more expensive to run models because you have more pixels to pass through your neural networks, right? And so this was really about trying to find, for customers, the trade-off point from their target performance versus the cost. And also to understand, you know, at the highest resolutions, what are kind of like the breaking points? Like, do we really get much of a benefit from going from 15 to 30 centimeter? And really, where is the breaking point on the lower resolution side, and why? So if we look at small objects like vehicles, you can see from top left to bottom right, the impact of going from high resolution to low resolution. You know, if we had to guess, I'm not sure. I'm curious if people can like write in the channel at what resolution they believe the modeling will break. I think that'd be really helpful. So we can take a second now if people can write in the chat their guesses. I think that'll be a pretty good exercise just to see where people are at. Okay, while people are doing that, we'll keep on chatting. So, okay, so how does the experiment work? Well, we built out an object detection model at 6 different spatial resolutions, right? We looked at everything from 7 centimeters down to 60 centimeters. And the 7 centimeter imagery was aerial imagery that was over Portland, Oregon. And the 30, 40, 50, and 60 centimeter imagery was simulated using what we call an emulator 5000, which is a way to synthetically generate subsequent resolutions. And the 15 centimeter imagery was actually generated with an HD process. That's a Maxar proprietary technology, but it's actually something that Fabio had already developed in the past. And we're roughly looking at about 10,000 labels that were created at the 7 centimeter imagery. And we automated the labeling of that process using a crowd labeling tool that we call Crowd AI. And also the labels were scaled to match the resolution offset in pixel space so that you didn't end up with outsized boxes or things like that. Like the data was fit for the resolution. We also made sure that we had consistent aerial coverage. So for the chips of different sizes, we made sure that whether it was sampled at 7 centimeters or 60 centimeters, it covered the same actual ground sampling, the same distance on the real Earth, right? And you can kind of see that on the right. We also made sure that the labels were relatively equal in number so that, you know, that we didn't have any, you know, models that were trained against chips that were just vastly different from one another. And then we did a histogram equalization, like a contrast limited adaptive histogram equalization. And that kind of like made sure that we were looking at apples to apples with respect to each individual pixel. All right, and then the model itself, we ended up using a YOLO V5 model, single stage detector. It was kind of, at the time, it was state-of-the-art performance on competitions like Kaggle and SpaceNet. And it has this property where it's kind of nice on small objects, which is good. We wanted to make sure we wrung every piece of information out, and we felt like this model would do that. And it also happened to be supported by the tech stack that we have, so that made it easy to run at scale. And then with the specifications, we roughly made sure that the specifications for each model at each resolution was fair and about the same across, and we made sure that the data augmentation was the same as well. So we did a kind of your usual suspects, mix up, up, down, left, right, flips, and mosaicing. And then, of course, we use your standard performance metrics to test the you know, the performance of the model. The performance of the the model against the task. All right, did we get any guesses? 30 centimeter, 40 centimeter, and 30 centimeter. Okay, that's cool. Interesting. So I'm going to pull up the first result. This is the average precision at the different resolutions. So I think what we find is that there is a cliff around 50 centimeters. So when you get worse resolution than 50 centimeters, the performance jumps just dramatically down. But what's kind of surprising is that as you go from 50 centimeter to 7 centimeters, you still get a significant improvement of performance across those resolutions. And even when you go from 15 centimeter to 7 centimeter, you're still getting a couple points here and there, but you know, it's not an enormous jump, but you're still seeing some informational improvement as you go up higher and higher. So I thought that was kind of an interesting result, if just because when we were looking at this original image over here, It's really surprising to me that when you go from like 30 centimeter to 7 centimeter, that it constitutes like almost an 8-point jump in performance. Because just looking at it as a human being, it almost seems quite identifiable. I think it does make a lot of sense that when you go from like 50 to 60 centimeters, it kind of just looks like a blob. And so, from an intuition perspective, I think that kind of lines up. And the other performance metrics, they sort of tracked, right? They had very similar characteristics, kind of when we got down to the 50 centimeter range, you have like very large jumps. The average precision across, from 0.5 to 0.95 was kind of strikingly linear though, in a lot of ways. So, I think there's still a fair bit of understanding that needs to go into this modeling to figure out some of the nuances there, but this did not quite track with the jump. The F1 score did, of course. But the question ultimately, when you look at this performance, is you want to get more into a qualitative space. So why do we think that, what are really the characteristics that are causing the model to perform more poorly? And what we found was that, for the most part, the imagery the model started doing more poorly when we got to the points where vehicles were closely spread apart. And so when you're going to something like a parking lot or something like that, the vehicles might be less than a meter apart or so, or significantly less than a meter apart. And so therefore your pixels start sampling across vehicles, and then it makes it really difficult for the filters within your neural network to accurately separate those models, right? Sorry, accurately separate those vehicles. So yeah, that's roughly the experiment we did. So why does this matter though in the context of the applied machine learning framework that we described? Well, even though we only trained 6 models technically, in order to get to those final 6 production models, we trained over 192 different models. And that was in our exploration phase around deciding what's the best parameters to be fair, in all of the data preparation components where we were trying to build many, many different types of models to see the impact that would have on modeling. There was an enormous amount of models that needed to be developed in order to get to a study like this. And now with the infrastructure that we have, you can conduct those studies, in weeks instead of months, and you can do it asynchronously. So you can set up the characteristics of an experiment, run it off on your infrastructure, and then you can go off and do a different model or project as your time allows. So that was sort of one of the big findings or outcomes of the modeling environment that we built. All right, well, what's next? What do we think is next for machine learning and remote sensing at Maxar? Well, we sort of see that there's these 3 large trends. The first is really the focus on data set engineering and synthetics. We're finding that the new state-of-the-art models over the previous ones are really only making performances of fractions of a percent and not really pushing the performance in a way that is going to really make a difference for our users. But what we do find is that when we pay a lot of attention and care into our data set engineering, and specifically into the synthetic generation of data, we're finding that these actually really do move the needle. And so we're putting a lot of effort and research into being able to very accurately engineer data sets and to create synthetic data. We're also trying to move towards just-in-time modeling instead of generating these global models that work everywhere. In the past, folks had really thought about modeling as, let's say if you're building a car detector, that you would like to build a car detector that works everywhere in the world with a single model. Well, we found that the world is not really wide sense stationary, meaning the statistics underlying the modeling changes quite dramatically from one place in the world to the next, and particularly from one season to the next. And so even if you do create a large scale temporal data set, it's very difficult for a single model to have the capacity to work well there. So what we figured was actually it's much better to build small models that you can train very rapidly on the order of minutes and seconds that kind of pull just the right data at the right time through the data set engineering approaches above, and create models that then, even if they overfit for a particular region, are perfect, give you perfect answers for that subregion. And so what that means is that it creates a focus on the data infrastructure that you have underlying all of this, so you can very rapidly train models at scale. And then finally, we're really working on walking up the knowledge tree from data points to knowledge. We sort of think of, our models that produce car detections, those are just kind of pieces of data. They're points of data, right? But what our customers really care about is answering questions like, if there was a hurricane, how do I, and I have a boat, how do I access different places in the world in order to help people, right? And so those questions are kind of more abstract than the question around where's the car, right? Or, what kind of car is that? And it's more about fusing these different kinds of data points into actual actionable information that you can go use in the real world. And you want to do that without creating a huge technical burden for people so they can, go and be effective in the world. Okay, and like I said, I think there's definitely quite a few things in machine learning and remote sensing coming up, particularly in the geospatial analytics world. But I think we would also love to hear from you as students of this and understand kind of, what's the next big thing and what's really important to you moving forward. So anyways, with that, I will close and just ask if anybody has any questions.
Thank you, Manny. I will open the floor here for questions. Are there any questions? Oh, they are so shy. You can also ask in Spanish.
Entiendo un poco, sí.
At least the questions probably you can answer in Spanish. Huh?
Yeah, puede ser. Con suerte.
Hello, congratulations for the presentation. It's very interesting. I am not expert in this kind of models, but I don't know if I understood well. I saw a very good performance for vehicle detection, but I understood that if you want to detect natural things, it's more difficult because of season and all that. And do you offer, for example, maybe you are doing, but I didn't understand, the code so the person from different parts of the world put the input and they obtain the model with the inference? That is why you are offering now? Okay.
Sí, entonces la idea es que tratamos de hacerlo muy fácil para que la gente ponga la información que quieren y después del otro lado viene las detecciones o las imágenes que quieren observar, ¿no? Pero estos códigos en unos 2-3 meses más o menos lo van a poner en el público para que gente pueda hacer ese tipo de encuesta.
Muchas gracias, buenísimo, gracias.
¿Otra pregunta? Yo tengo una listita. Pero bueno, un poco en línea con lo que Anabela preguntaba, quería saber si esta plataforma que vos nos mostrabas, si hay como un usuario, un demo o algo así que se pueda probar, o si es algo que más bien son ustedes, que solamente ustedes usan y después ponen a disposición únicamente el modelito entrenado, digamos.
Sí, sí. Por ahora es una plataforma interna, pero lo que quiero hacer es hacer open source, ¿no? En como 4 meses más o menos. Por ahí en enero o algo así, en febrero, por ahí. Vamos a buscar sacar. Porque lo que hace es lo hace muy fácil para elegir las imágenes que querés, ¿no? Y de esa forma acelera el research, ¿no?
Exacto. Sí, yo lo que veía ahí, que también era la otra pregunta, digamos, era cuando vos elegís, cuando vos entras a la plataforma, ya esos como todos los metadatos, esa ayuda ya está cargada en la notebook y entonces vos después solo cambiás lo que querés, digamos.
Ajá. Sí, sí. Está todo cargado y después si querés imágenes que obviamente no tenés en tu computadora, lo puedes requerir y te lo hace el download, ¿no?
Ujú. Y si no lo querés bajar, ¿eso queda en tu S3 bucket? O... Sí.
Exacto.
Ok. Y de ahí lo puedes procesar, digamos.
Ajá. Del S3 sí puedes hacer streaming, como a QGIS o lo que sea, ¿no?
Ujú.
Ujú.
Ok. No, ya está. Y la última pregunta era, o un comentario más bien, esto que hablabas al final
Ujú.
de los just-in-time models,
Ujú.
que tiene su parte súper buena, pero a la vez, lo mencionaste, ¿no? Esto del overfit, que es
Ujú.
muy fácil con Machine Learning, porque
Ujú.
van a aprender exactamente los datos que vos le des. Entonces, en ese sentido, y es como, porque acá son, la mayoría somos o son estudiantes de maestría y doctorado,
Ajá.
como, bueno, aclarar esto, ¿no? De que, digamos, si uno le da datos malos, el modelo aprende de esos datos malos. Entonces, en ese caso, para un just-in-time models,
Ujú.
tenés que estar 100% sure
Y
de que
sí,
tus datos son buenos,
y sí, no, sí.
de que primero
Absolutamente.
los filtraste
Ujú.
como corresponde para que realmente después predigan lo que
Ujú.
vos querés, ¿no?
Sí, y lo que haces es bajas la complejidad de los modelos, ¿no? Para poder hacerlo muy rápido, pero también bajas la complejidad del modelo, de la información abajo de todo que estás tratando de modelar, ¿no? Lo que quiere decir es que por ahí ese modelo no anda en otro lugar, otro de ese específicamente lugar que es donde estás buscando, ¿no? Y bueno, para hacer eso también es algo que tenés que tratar con datos nuevos para asegurarte que de verdad están andando bien, ¿no? Entonces, cuando haces el just-in-time modeling, también todavía te fijas en una porción de esos datos que entran, que son nuevos, para asegurarte que the performance es bueno, como se dice.
Sí, sí, que la precisión es buena o la performance, sí.
Exacto, exacto. Entonces, por ahí en ese momento no estás haciendo por mano 100%, pero estás haciendo los 5 o 10% para asegurarte. Y después, cuando estás seguro de que anda bien, lo puedes dejar y que vaya, ¿no?
¿Alguna otra pregunta?
Hola, ¿qué tal? Muchas gracias, Manuel, por toda tu charla. Quería consultarte sobre lo que nombraste de la generación sintética de datos.
Ujú.
Si podrías comentar algo corto en qué sentido iba y para qué uso. Gracias.
Sí. Bueno, hay muchas formas de datos sintéticos, ¿no? De alguna manera, el generación de datos sintéticos perfecto sería que creas una imagen exactamente como una imagen real, pero le das, por ejemplo, información en qué pasa en cada parte. Entonces, por ejemplo, le das el mapa de Google Maps y genera una imagen de satélite, de así, ¿no? Hay otra forma de sintética, bueno, eso sería interesante porque lo ves y parece como datos reales, ¿no? Pero hay otra forma de sintético donde vos tenés un modelo de un objeto, por ejemplo, y lo pones en la imagen y usas un GAN, ¿no? Un Generalized Adversarial Network, para hacer una imagen de ese modelo y una imagen abajo parecer tan real como otra imagen verdadero, ¿no? Entonces, de esa manera puedes poner modelos de objetos que por ahí son muy extraños, no se encuentran muy seguido, ¿no? Por ejemplo, si vos querés hacer un modelo que encuentra, qué sé yo, ¿cómo se dice? Un estadio de fútbol en los Estados Unidos que no se encuentran porque nadie acá juega al fútbol. Por ahí tenés que crear un modelo sintético que lo pones sobre diferentes imágenes y después usas el GAN para crear una imagen verdadera o similar a una imagen verdadera. Y después de esa manera puedes crear modelos que son mucho más grandes, que están puedes crear datos, un dataset que es mucho más grande, que se ve en diferentes formas que es muy difícil observar en la naturaleza, ¿no?
O sea, no sería solo como estos que solamente, no sé, flipeas la imagen, la rotás y demás, sino que además generas imágenes como composiciones nuevas de esos objetos.
Exacto. Y por ejemplo, una cosa que cambia mucho es la dirección en que viene el sol, ¿no? Y esa crea una sombra diferente. Bueno, de esa manera, si pones este estadio en un lugar diferente, en otra foto que hay la dirección de la luz viene de otro lado, el GAN también crea la sombra que por ahí no se encuentra muy seguido. Por ahí lo ves de otra forma que es muy difícil encontrar en la naturaleza.
Claro. Gracias, Mani.
¿Mm?
¿Alguna otra pregunta? Aprovechen que castellano. Bueno, les voy a preguntar yo, a ver si a mí me responden. ¿Han usado ya algo de Machine Learning? Sí. ¿En la maestría algo? ¿Un modelito? Algunos. Ok, bueno. Capaz después te consultan, Mani, entonces.
Bueno, creo que tienen mi email, entonces siempre estamos buscando a gente con quien laburar, por supuesto.
Sí. Lo único que, claro, acá cuando uno hace una maestría o un doctorado, es uno solito el que cumple el rol de las 150 personas que tenés vos.
Y bueno, tienes razón. No, pero es un tiempo muy interesante en Machine Learning, ¿no? De esa manera que hay tanto espacio para estudiar y ver que hay mucha gente que nunca lo he pensado, ¿no? Entonces, una persona puede tener un impacto enorme. Y te digo que de esas 150 personas, no son todos genios, ¿no? Entonces, siempre estamos buscando.
Acá tampoco.
Ahí está.
Ok. Bueno, si no hay ninguna otra pregunta, entonces sí.
Fabio.
Hey, Veronica. Veronica, this is Fabio.
Sí.
I don't know if you can hear me. I have a question for Manny. I don't know if he covered these, but so
Just
most of the
give me 1 minute because
Yep.
one of the students will ask and then I give you the
Perfect.
floor. Is that okay?
Hola, gracias por la presentación. Te quería consultar, en las GANs, ¿utilizan el espacio latente o les interesa para algo? ¿Se extraen algún tipo de clasificación de ahí?
Absolutamente. El espacio latente de los GANs se puede usar para entender las características de los datos, ¿no? De alguna manera lo pasas una imagen y eso lo comprime a nada más unos datos más informativos, ¿no? Entonces, si vos pasás todas tus imágenes por ese sistema y sacás la información latente, ese espacio latente, eso se puede usar para comparar las imágenes de una forma más ¿cómo se dice? Más informativo de que comparar los píxeles directamente o usar algún otro modelo que por ahí no es tan específico. No sé si lo traducí bien.
¿Se respondió?
Okay.
Ok, gracias, Manny. Fabio?
Yeah, it's just more like a comment for Manny, and so most of the people in the audience are students, I'm assuming. So they will need to get a job in the next, few years.
Yeah.
What are the skill sets that you think are necessary right now and the next 3 years? Like I can think about Python, PyTorch, if they want to get into deep learning, AWS. What else?
Yeah, so those are the big ones, right? So Python, Jupyter, AWS. But I think the most important thing that you can do is to continue to have a growing mindset. So to continue to think about how rapidly things are changing within the industry and to never stop reading and integrating that information so that you can kind of hit the next target, right? So, I think, Fabio, you deal with this all the time too, right? What's the next way to think about, atmospheric compensation, or what's the next way to create a better HD that is that is actually true to real information, right? So I think that's even more so true in machine learning because it's changing so rapidly. In terms of specifics, like aside from the tools, the knowledge base, I think synthetics is an enormous thing. GANs is an enormous thing. Transformer networks is an enormous thing. And then also moving forward across the integration in time. So how do we not just look at a single shot of a single image, but how do we look at time and samples within time? Because that is a really difficult space right now. It's very difficult for people to do that in a computationally efficient way. And there's a lot of research in it now, I think, that's going to be very important moving forward.
Yeah, indeed, for forecasting. I mean, we really need precise forecastings.
Oh, yeah. It's, it's funny, in space, we're very quantized, right? A pixel is a pixel and it's quantized, right? In time, it's continuous. And so, and we don't always get to choose how the sampling happens, right? With an image from space, you might get an image on Tuesday, and then 3 weeks later, it'll be cloudy. And then the 4th week, maybe on a Wednesday, it'll be, so how do you deal with that odd temporal sampling? It's not always so regular, right?
Yeah, right. Mm-hmm. Good. So did you take notes, guys? Open mind, growing mindset.
That's good. Yeah. We're also, the other thing you can do is work in Maxar. I mean, there's lots of interesting things going on here. So
good. You're based in the USA?
Yeah, I'm in Virginia.
Yeah. Okay, there's a question there in the chat.
Oh.
People just need some time. Which would be the learning path to understand the whole pipeline?
Yeah. So Docker, yes. I would say Python. I would say Terraform or Kubernetes, Terraform, Helm, and then I would say I personally like PyTorch, and then I would say PyTorch Lightning is really good too. So that would kind of get you probably all of the pieces together.
There were some abbreviations that people do not know here. If you can type them down in the chat.
Oh, sure. Yeah, which ones?
Like you said something like AML, ML.
Oh yeah, applied machine learning.
Okay. Terraform, what's that? What's Terraform?
Yeah, so Terraform is a tool that lets you rapidly build infrastructure on AWS. So instead of like literally spinning up a machine in AWS, you can actually write that as a script, and Terraform allows you to build up databases and compute resources and things like that.
Okay. To put everything together like.
Yeah, automatically.
Perfect. Yeah, there's a translator there.
There you go. Infrastructure como código, exactly.
Okay, we have one more question.
Oh, yeah. So estamos tratando de hacer data frames como infraestructura. Entonces, pero...
Manuel, una pregunta más.
Ajá.
Acerca de... Bueno, hay un cambio que se está dando en varias cosas en programación que es R y Python, y como que es una guerra que termina ganando Python, parece, al menos en muchas cosas. Si podés decir algo de ese punto.
Sí, sí.
La segunda, te tiro 3, a ver si está bien, para ahí las hacer a todos juntos. La segunda es sobre Shiny, aplicaciones que originalmente era una librería de R, pero ahora también se está pasando a Python. Y la tercera cosa, que es algo que está por fuera de programación, que es la coordinación en equipos, porque nosotros somos uno solo que hace las 200 tareas, pero ustedes que son 150, ¿qué usan para coordinar? Y entre ustedes se me ocurre algo como Scrum, por ejemplo, pero si podés decir algo de esas tres cosas, entre R, Shiny y cómo coordinan entre ustedes los grupos.
Bueno, la primera de R versus Python. Bueno, para mí acá se encuentra que los científicos, la gente que estudia estadística o física o cosas así. En general se usa mucho más el R, ¿no? Pero cuando la gente van de ese lugar de research y se mueven mucho más a las aplicaciones, es mucho más común que se encuentran que usan Python. Para mí, la diferencia no importa tanto como la cantidad de gente que lo usan para tus aplicaciones, ¿no? Si hay poca gente que usan esa lengua para tus aplicaciones, obviamente no vas a poder encontrar muchas libraries que te ayudan a hacer lo que estás tratando de hacer, ¿no? Entonces, de esa forma, por eso nosotros usamos Python mucho más para las aplicaciones en producción, ¿no? Pero como dije, el R tiene muchos paquetes que son muy buenas, que andan muy bien, pero si no hay tanta gente que lo usa en producción, es muy difícil para usarlo. Shiny no conozco Shiny, desafortunadamente, pero cuando hablamos de la coordinación de equipos, en general nosotros usamos Agile y Scrum, usamos Confluence y Jira. So, son usados muchos para los equipos que quieren coordinar con otros equipos, y lo hace muy fácil. En general, nuestros equipos tenemos un Program Manager, una persona que maneja el Agile, y después tenemos un equipo técnico que laburan con ellos para hacerlo fácil.
Manny, ahí un chico pregunta por qué no Spark como una de las habilidades.
Sí, sí.
Y ya dejó hablar a Diego.
Sí, se encuentra mucho Spark ahora también en diferentes lugares, pero yo en particular no lo he usado mucho, pero oigo buenas cosas. Entonces, si vos alguna vez mirás a la lista de diferentes tecnologías para hacer cosas en scale, ¿no? Es enorme, entonces no puedes tratarlos todos.
Solo para aclarar, eso de Shiny es también como un paquete de R que ahora está permitiendo el uso de Python para hacer tipo web applications, ¿sí? Donde simplemente pones online alguna aplicación para hacer cosas, o incluso tipo dashboards y cosas así, también se pueden poner.
Qué bien.
Ahí.
Viste, estoy aprendiendo algo yo también.
Vamos. Diego Rivera, que levantó la mano, no sé si querés hacer una pregunta, escribirla en el chat o querés hacer un comentario.
No, gracias. Quería hacer una pregunta. Muchas gracias, Manuel, y al Gulish también por estas buenas ponencias. No, solo contarte, uno que viene de la geografía se ha enfrentado a muchos desafíos porque la programación está metiéndose en todo y nos hemos visto obligados a aprender mucho de programación, de cloud computing, cosas como el machine learning son para muchos de nosotros muy nuevas. Mi pregunta tiene que ver con cómo todas estas tecnologías que están creciendo están aseguradas en un futuro, dado que, por ejemplo, el cloud computing hoy en día, como Google Earth Engine, o veo también como lo hacen ustedes en Maxar, son empresas privadas que están proveyendo este servicio actualmente, pero uno tiene el temor de decir, bueno, en el futuro va a seguir siendo así, ¿vale la pena meterse en eso? ¿Vamos a tener posibilidad en un futuro de seguir utilizando esta librería y estas capacidades? Eso simplemente no. Manuel, gracias.
Sí, en la vida nunca hay cosas aseguradas, ¿no? No sabía que íbamos a ser tan filosóficos. Pero yo creo que AWS y Azure son dos cosas, y GCP, Google Cloud Platform, son tres formas de cloud computing que, por supuesto, por lo menos por los próximos 10 años, no creo que se van a ir en algún lugar. Y también si empezás a usar cosas como infrastructure, como código, que empezás a usar Terraform y Helm y cosas así, creo que eso te protege de los cambios del lado de la gente que crean la tecnología de cloud, ¿no? De esa manera, nada más hay nada más pocas formas de cual querés crear una computadora y poner información adentro de esa computadora, ¿no? Entonces, si invertís mucho más en cosas como Terraform y de esa manera, eso te protege un poco del cloud provider abajo, ¿no? Pero como dije, nunca, la vida siempre va a tener tiempo para aprender nuevas cosas porque no te va a dejar quedarte cómodo con una tecnología nada más. Siempre está cambiando. En particular acá con el machine learning. Para mí, por ejemplo, yo aprendí el deep learning en 2004 2014, ¿no? Y yo empecé con Geospatial Deep Learning, ¿no? Y en esa época no había TensorFlow, no había Keras, no había PyTorch, no había, viste, todo esto, PyTorch Lightning, nada así. Entonces, yo tuve que escribir mi propia forma de Keras sobre Café, ¿no? Y después, en los últimos 7 años, cambié de eso a TensorFlow, a PyTorch y ahora PyTorch Lightning, ¿no? Entonces, la única cosa que es por seguro que va a cambiar. Pero eso es laburo de científico y de ingeniero, ¿no?
Totalmente. Por eso lo de Growing Mindset. Me gustó mucho ese consejo. Bueno, Mani, te agradecemos enormemente. Muy, muy linda la charla, muy interesante.
Gracias, me divertí bastante. Bueno, adiós.
Bueno, que tengas linda tarde por allá, no sé qué es.
Sí, tarde. Adiós.
Hasta luego, nos vemos.